asked and kind of prodded to spend a little more time getting, let me pull this up here, spend a little more time getting a better plan of action on how our class is going to progress. Going off of what Ken had and what I see, how I see this class progressing, and you guys may already agree from the amount of jumping around in this book that we have to do. I don't like it. I don't like having to start and read one little section out of this one and then jump to the next 10 chapters down and read a section out of that and then go back to the next stuff before. I don't like doing that. And I don't know if you guys do, but I don't think it works. I don't think it works to have to jump all around. So what I'm wanting to do, and I'm going to have you guys kind of help me figure out if it's possible, is I'm wanting to maybe rearrange the course schedule a little bit to get us somewhat of a linear progression. I think that Charlie's been talking a lot about that. And I want you guys to have a defined start and a stop point that's clear. Where's our remote at? And I may want to change things around a little bit from what we talked about in the syllabus. But I don't know. I'm kind of looking for a little bit of your guys' input because I know this last week we had to start in section 24, read a little bit in there, and then we had to move out of there and go into a different section. What was it, 41 or something like that? Anybody read it? I hope so. Yeah, 34 and 41. And then next week we got to do the same dang thing. What I'm wanting to happen, and I know Charlie's kind of also wanting this to happen, is that when we start in this process of this class, I wanted to start at the beginning of a chapter. Like that, for instance, unit 41 here. You guys told me the other day that you guys haven't really spent any time with resistors. Well, there's a buttload of resistors on your guys' circuit boards. And granted, a lot of the time, if you see a blown out resistor on a circuit board, the most likely thing that you're going to do is just change out the board. But there is an opportunity for us, if we're in a service industry, that, say for instance, we want to, we see a blown out board, but we don't have a board available to us. So then what do? Well, we do our best to fix the board that we have there. And a lot of times if a resistor is blown out, it's a couple of pieces of solder and a new resistor that costs you 14 cents from Chris Supply and you save the day. So it's difficult for me to want to just skip over some of this stuff, especially when I'm trying to learn as I go along with you guys, to where instead of jumping, okay, today what we talked about, well, so far we've talked about line voltage thermostats, low voltage thermostats, pressure switches, and today, from what I can gather from what Ken had, he wanted us to start talking about relays. So that's all great and everything, but why not talk about them in the line that we actually have here, so whenever it comes to test time, I can tell you guys, hey, review unit 34, 1 through 16. Instead of, okay, spend an hour trying to figure out what we got to review and then still not sure if we have everything. That's where I'm coming from on this. And would you guys have any input on that? Like, is that how you would rather see this go, or are you okay with jumping around?
I was wondering why we're not using electricity.
I'm wondering too. Yeah, I'm wondering too. I don't know. I can't answer that because, let me pull this up for you. Let me get what. So this is what Ken had planned for this class. And when I don't know, you guys weren't here the other day when Ken came in. It was quite the experience for me.
Oh, you met him too?
Yeah, I got to meet him. It was quite, well, it seems like him and Charlie are maybe cut from the same cloth. Like they seem like they're very fast talkers and they have a lot of information happening all the time. It was interesting being in the middle of those two going off. It's kind of fun just sitting back and watching the show.
Charlie finishes sentences though.
That's the good thing about him. Whoops, that ain't the one I wanted, is it? Yeah, it is. Okay, let me bring this over. All right. So far, we've had low voltage thermostats, and then we had this lab examining low voltage thermostats. Then we've had pressure switches, and I hope we can. Did you guys find any more information on the pressure switches? Anybody? Nobody got an email back. Sam? Yeah, you're Sam or Seth? Sam. Seth's your middle name?
Oh, Sam.
That's why I get confused. Two S's. So Sam, anybody? Anything? Okay. I know you aren't anything for that. But
I even said I was a student.
nothing, huh? Okay. Well, I'm not going to fault you guys for that. That's kind of my fault for not having box pressure switches or shit available for you guys to look at. I don't have access to your guys' budget to be able to go out and buy a pressure switch, a new one in the box. So I did the best I could with having the ones that we have in the lab that you guys are actually going to see on units. So I'll talk with you to get you caught up on that. But I think the best thing that we got out of there was when you guys found the cover for the Renco pressure switch, and I'll probably just have you go through that as a makeup for your lab. But what I want to do is this. I want to eliminate this. I want to eliminate 34, 13, 14, 34, 14, 34, 15, and then jumping around. So if I can follow this flow right here, we spent time in our lab books. Let's see, this one right here. We started with what, 34.2 or something like that? Yep, 34.2. We did that, and then we did 34 pressure switches, 34.4. We didn't spend any time with line voltage because there's not a lot to be had there. But today, what I think his intention is for us to start with the identification of relay and contactor parts, and then maybe even overloads. That's not even what we got going on there. So this is what his plan is for here already. And I don't even think that is the right plan. So what he has scheduled for me to talk about today is contactors, but it's not matching up with this right here. So that's where I'm at right now, is that I'm trying to make this streamlined for you guys to be able to, all right, here's point A. We started this semester with examining low voltage thermostats. And we're just going to work through this part until we get to a spot where it's like, all right, we know what the foundations of identifying relay and contactor parts. Now let's go put those to work. Let's go actually put our hands on installing them, or go out in the shop and mess with them, figure them out a little bit. That's what I'm kind of thinking. And this is going to give us a little bit easier ability to plan forward, like somebody's got to be gone today. And Elko's kind of driving it with his situation right now. I have to plan the entire amount of what we're going to cover in class like the day before. Once we finish up today, I start working on what we're going to talk about Thursday, and trying to get you guys, okay, well, here's another added list of confusion. So this book isn't even the same book that this stuff is coming out of. It's from the older version of this book. So this stuff right here is all matched up because I've gone through with the old book and the new book and matched them up, so we have some coherent stuff here. That's obviously not your guys' problem. But what I'm trying to say is, do you guys have any ideas of how we can, we have this goal that's our master syllabus, and it's to get you guys where we expect to come out of here. But are you guys okay if we deviate away from this a little bit and say, hey, look, this isn't making sense, Brian. Why are we jumping around in this book? Why can't we start from here and go there?
I think we're all fine with how you want to read it.
Yeah. Well, I just, that's what I'm at. What?
We're allowed to build it better.
I think so too.
Yeah, you set it up to where how you can come up with troubles or something.
Absolutely.
That you would go through.
Right.
You teach us the those steps.
Sure.
I think that would be kind of cool because we can kind of get an idea.
Yeah, absolutely. And that's the that's kind of the larger picture of what we're trying to identify, Charlie and I, is that, okay, you guys started with this book here, right? So that's cool. I'm glad you did, and well, there's some good stuff in here, but I have you guys starting with this book at first semester, and now I have my fourth semester guys using this book. So it's like, holy guacamole, not even all of them have this. So it's just trying to get it to be start from A, go to B, and then to C, and then to D, instead of start at A and then move to F, and then back to C, and then jump all around.
Well, it wasn't like it would be like a week time, because his assignment was to answer a few questions in a review after a certain section. He might not get to covering that material for like 3 or 4.
So he would,
3 or 4 days. So if I had a question about understanding something in there, by the time we get to covering it, forgot something else.
sure, and then where's the benefit in that for you? No, okay. Well, this is where I'm kind of leaning. So what he's got going here is he's got, and what's actually all driving this, first of all, the Elko thing, but I have to get you guys some grades. We've got good labs. Everybody that's been here participated in the labs and had a smile on their face has gotten 100%. So that's good. I don't expect you guys not to have that. But when we're talking about taking some tests, this is kind of what I'm understanding is that what he's wanting us to, I haven't found any of his tests. So the tests that we take will be probably my creations unless I stumble upon them. But even then, I can't really test you guys on something that Keith was going to talk, or Kevin was going to talk about if I could talk about it. So I think maybe that's what we'll just have to start doing is we'll spend a little more time. Today we're going to talk about contactors and relays and do a little review. And then what I would like to do on Thursday is I will spend some time combining all of what we've talked about so far up to Thursday. So finishing up with today, I'll spend some time combining all of the high points, and we'll spend a little bit of time, probably we could even spend up to an hour if you wanted, but spend some time reviewing and making sure that 100% on everything that we've talked to up till that point. Take a test after we review, and then we'll kind of reset and talk about moving forward in a more linear way instead of jumping all around. I feel like that's going to probably be the easiest way for us to break off of what we got happening now and move forward. So
You're in a pretty unfortunate spot, both you and Charlie, but I mean, we'll be patient with you guys, and I'm pretty sure everybody else agrees with me.
yeah, I get that I have a way out, but that doesn't matter to you. You know, you still paid for class, so what's my job to get my shit together and make sure that you guys get what we promised you in the master syllabus. So, and I'll do it, and we'll get it going here. So okay. Well, thank you for listening to that, and I appreciate your input. I definitely think that once, like, as you guys, if you decide to come back with us in the spring, I think we're definitely going to have a much better program moving forward once we get all of this shit ironed out here. So I guess we can be done talking about that. If you guys have any input on how you would like to see this progress, please let me know, because I'll definitely tailor it to what you guys want to know, just because of the shitty spot that you're in. You know, you guys want to see the master syllabus again, just so you're familiar with what our goal is, just so you guys can have it in your brain. I can pull it up quick. Let's just do it. Let's stop talking about it and do it. All right. So what my promise to you is the student learning outcomes right here. Apply advanced principles of voltage and current to HVAC components. And that's what we're starting to do right now. We're learning about the pressure switches, the thermostats, and the contactors. Differentiates the characteristics of loads and control devices. Start to do that as we start talking about motors. The troubleshooting part, That's gonna come into place once right now we're learning the foundations of what we're gonna troubleshoot, and then once we get that under the way, that'll help us to be able to just go through and measure circuits. Safety protocols, if we get on into that, we're gonna make sure that we're safe. And then to evaluate appropriate measuring techniques for HVAC repair. So that's just gonna be with me, it's gonna be with your meters. So I'm not gonna be able to help you out with your gauges or anything, but I'll definitely tell you everything you want to know about your meters. So that's what our goal is out of this. And I think we're on the way right now, but we're gonna make it that and so much more. So, all right, thanks for listening to me about that. Please, if you have any kind of comments or if you want to see things go a little different, let me know, because we'll definitely change it to make you guys happy. So, just talking about our buzzword linear progression.
Yeah, it's been pretty non-linear so far.
Yeah, and that's a big problem for us stepping in, not being inside of Ken's brain to fill in the pieces.
And not being able to reach through the phone to the publisher, literally strangle them.
Yeah, we're still having trouble
Just
getting
wasted
even
20
material.
minutes of my life going nowhere on that. So I really do not like this publisher.
All right.
If you want to stick with the book, that's fine.
No, you're the boss, man.
I don't know. Have you looked at that other one?
Only if I need to. Okay, let's quit whining and get moving here, huh? Who's okay with that?
So is that a test or something?
I'll put it in as a test, but I promise you that you don't have to be worried about it. We will cover everything and more in the review, and then we will talk about it. We'll talk about it in the review and move right into the test. And so bring your computers. I'll have it all set up online so we can just, once we get done talking about it, bring it right up and multiple choice. So electrical components is where we are today. Transition animation from beginning. All right, got some nice orange and blue fire there for us. Super sweet. Okay, so part of the other thing of what I got going on, I'm going to exit out of this real quick and just make sure that we're still doing this, is you guys can't see it, but I'm starting to record what we're talking about. There's a little guy there for us. So what my goal is going to be is to have all of these discussions that we have during class be available to go over and review. And this is going to be hopefully the best one yet since I'm learning. Okay, we are screen sharing. We are going to start this. And okay, so here we are, electrical components. So I spend a little bit of time getting out in front of where we talked about we were the other day. So I wanted to just, as we keep moving the way that Keith wanted us, Ken, why do I keep calling Keith? It has Keith in my brain for some reason. You guys hear me talk about Keith, it's Ken, all right? So let's just pretend he's Keith. So the other day was we just talked about, hey, Brian never even spent any time with resistors. So that's the very first thing that we're going to talk about today, is we're going to talk about resistors. Resistors are commonly found throughout the HVAC industry. You'll most likely see them on circuit boards. Its measurement is the ohm, and they are commonly used to limit current in a circuit. So there's what they look like. I have a bunch of them in our little HVAC file here. I don't know, have you guys you can put your fingers on these? No. Okay. So let's see. So when we're talking about resistors, we have these little guys that are showing up on the screen. Here's one. Send that guy around. And you'll notice when you look at these, they all have the little color codes on them. And that's pretty common for the smaller ones, is to all have a little color code on them. And what that color code means is that when we're figuring these out, they're numbered. So on this one that we have up here on the board, we have a brown, a green, a red, and a purple on there. So if I were to follow our little guy out here, it would say our first number is going to be brown, so it's going to be a 1. Our second is going to be green, so it's going to be 15, 1-5. And this is all for the rating of the resistance in this particular resistor. So the first one's going to be 1, 5, and then we have the third one is going to be our multiplier, and it's red. So we find the multiplier column here, and we find the red, so it's going to be 15 times 100. And then this last one here is the tolerance, and that's when you put the tolerance means when you put your meter on here, it's going to be 15, what is that, 15K? Probably 15K ohms, I think so. It's going to have, it'll be, put your meter on there, it'll be 15K plus or minus purple 0.01%. So that's a pretty exact measurement that we're going to see there. And when we get past this part here, I would like us to even throw our meters on there, and we'll just check and see how close they are to what we figure out. So we can do that in our lab. I got a few more here too we can look at. But something else that I want to include into this that you guys will definitely see that I don't have a picture of is what is this. This right here is called a potentiometer. And it's very much the same thing as a resistor, except for this one's not a fixed resistor, it's an adjustable resistor. So as we move the little screw here, I should put a picture up there, but it's no big deal. We can increase or decrease the resistance in the circuit. And these you find a lot on electric heat, especially like single units, coal heaters before. They've been just an enclosed potentiometer that you can increase or decrease the resistance in the circuit for you want to have what different types of heat that you want. So this right here, the symbol that we have up here is the symbol. Oh, you guys can't see it when I do it. It's that electrical symbol for what we see in electrical drawings. And I believe it's very similar. It may just be a square for HVAC drawings. It may just be a square with a resistance value next to the square. Like it might be something like this. Or I guess this would be a rectangle, and then it may have a resistance value in here, or it may be up here. That's what you will expect to see in your print. Something similar to that, or something like that. Usually on a schematic, they will always have a resistance value around it, so you don't have to measure it out. So we talked the other day about a diode a little bit, didn't we? Talked about it, mentioned it. Well, what is it? A diode is a device that's commonly used to control the direction of current flow in a circuit. They're also commonly found in HVAC circuit boards. Diodes are also used to convert AC voltage to DC voltage in what's called a rectifier. A rectifier in here, but I do have several diodes. So this is what you guys would be experiencing if you were to, in your circuitry, to convert a AC voltage like a low voltage. If you wanted to convert from your transformer, we would feed with the transformer. If we wanted to make 24 volts DC, we would start bringing 120 or 240 into our transformer, transform down to 24, and then with this rectifier, there will be a little bit of loss because of the translation. But we've put 4 of these diodes. That's an example of a diode. That's not the same as that one. But we'll put 4 of those diodes in a configuration that we'll learn about a little later. Where's another diode? I think that one looks just like that. This might be a diode here. This is a huge one. Yeah. Where in the world did my little diode go? Here it is. Here's my actual diode. Here's the actual picture right there. Here, this big bugger, that's also a diode. This is one that we pulled out of the shovel somewhere. So pretty much the same thing. It's just directional directional current and voltage flow. The direction of how this is going to go through here, it's going to allow the voltage to travel through this side, but block it when it tries to come through that side. So,
I got a question about those small resistors.
yeah,
How do you know what side to start on as far as the color goes?
I think it's always left to right.
Which side is that?
Yeah, which side? Let's see. That's a tough question.
I know one has to be on top of the actual, the left side.
Let's go back. Let's go back up there and we'll look at it. Wrong way. Yeah, I think so. I think that's exactly what we're gonna do. Yeah,
Okay.
that's what I was about to say, is that the tolerance band is usually all the way down here at the end, and most of the ones that I've ever seen have been the silver and gold, have been plus or minus 5% and plus or minus 10%. So I would always just see that and just assume that it would be going the opposite direction. Have that information. So yeah, definitely. If he's reading the book, he's probably right. So
That makes sense.
yeah. Yeah. You can just keep going on. Okay, so we talked about resistor, and we talked about a diode. And I guess since you are following along in the book there a little bit, I kind of jumped around a little bit. What I'm kind of trying to do is I'm trying to catch us up a little bit and then keep moving forward with what Keith had. So that's our, damn it. All right, sorry. I can't get it, guys. I just can't do it.
Write his
Okay.
name on the board 10 times.
Well, it's right there.
You
And I
need to
looked
write
at it already.
You need to write it.
Yeah. Yeah. So, and this is the, yeah, geez. All right. So, and here's the symbol. Here's the symbol. This is kind of a nice, oh, darn it. Why does it do that? So this is a nice symbol here that kind of shows you the direction of the symbol with the circle on that, or excuse me, with the little gray circular, what is that called? Little gray circle on the end, little gray band on the end. All right, and now SCR. Similar to a diode in the fact that it only connects in one direction, an SCR header has what's known as a gate, and that's similar to electronic switch. The conversion of AC voltage to DC voltage is in what is called a converter. So let me see where our SCR is. Here's our SCR. Here it is in all of its glory. Little tiny bugger. But what this is going to do is that it's also used in AC voltage and current, but especially to convert AC to DC. But especially if we need to have a circuit that allows the flow of current at a particular time, this is what we could use because we can actually turn this little directional diode on and off. With the, I think the gate is usually always in the middle on this guy. Whoop. But also, conversely, this is an SCR. This is one of the ones that we use in the shovels for converting the high voltages to AC to DC. Right here. Here's it's kind of hard to see, but here we have we set this guy up. This is going to be the anode, so this is going to point this way. The cathode, and here's this little white wire down here is going to be the gate. That's going to be what we set this off with. So it's a big old hockey puck there. There's depending on the type of converter that you. We'll spend some time if we ever talk about DC. I don't know if that's in our plan, but depending on the converter that you get to, there could be up to 12 of those in line with the three-phase power to convert the AC to DC. So now we're going to go backwards again. I guess it would, depending on how we originally wanted to progress. We're going to talk about transformer design. Are you guys familiar with what's called induction? You ever heard of that? Great word. Basically, just what's happening right here inside of this. This is what's called induction that's happening. That's turning the 120 volts, or even though they're not electrically connected at all, that process that the electrons are jumping off from here to here, it's called induction. And it's basically what's happening inside of every transformer. That's how we can reduce the voltage from 120 up here to 24 down here. With that induction. So primary and secondary voltages transformer right there. Primary voltage of the transformer depends on the tap use. So some of these, has Charlie drawn you transformer taps up here? No? Okay. We can do that. Let me read this part. And this one right here is a variable auto transformer. I would assume that that's going to be very similar to what's the potentiometer, to where this adjustment, basically it's a little arm down here on the secondary side. It's going to allow you to, wherever you turn the arm, it's going to allow you to adjust the voltage by turning that arm on this coil, where you can either add the coil or reduce the coil to get your higher or lower voltage. That's what I would assume that is. So
What's that writing? Under the numbers, it says percentage of.
this guy,
Yeah, on the one right there.
or the rest, down here,
Oh, the numbers on the.
On the gauge.
Actual.
percentage of output voltage, I would imagine that says. Percentage of the maximum output voltage. So, yeah, I don't know about those. I don't know about auto transformers. It seems to be fairly evident that it's just an adjustable voltage supply. So. Depending using the different settings, different areas of the coil that's going to touch inside of there.
These will cover to.
Listen to you with your jive talk. Okay. Anybody have any questions on transformer design? I didn't think so. Transformers are pretty neat, but they're kind of simple. So, transformer application and construction. You guys have seen these out there on the poles. A lot of ones that we're moving to today are all the big green underground ones. A lot of them floating around because it seems like underground services are a lot easier to maintain than overhead stuff. You guys have spent a bunch of time with these, I'm sure. Control voltage transformers, dropping 120 down to 24 for your thermostats. This is something that I doubt you guys are going to spend a lot of time with, but something that we see occasionally in our world is called eddy current. And eddy current is as the voltage and current are rotating around this particular deal here. The space in between the coil lines. So let me just draw them. So on our, this is going to be our, let's just do it for, this is just going to be, we're pretending this is an electromagnet. So we're going to have our coils. So these coils are fairly far stretched out. They're not very tight. And when we're talking eddy currents, the direction of this current flow, so the positive is going to be going this way, it's going to be coming out this way. How the magnetism and the induction happens in this is that as the current is here, the magnetic lines of flux are expanding out around here as this is flowing through. And let me see. As this happens, we have little lines that are coming out here like this that are invisible. Current flow. When they're talking about eddy current, it's in when these are spread far apart, these lines aren't matching up good enough to stay in the same flow. So we want, when they're far apart, it's harder for them to stay going the same direction, the magnetic lines for induction. Far apart, they start to spiral against each other, and that's what an eddy current is. So if we were looking straight at the end of these two wires, we would have wire here, or yeah, these are wires on the coil. Have wire here and wire, let's see, we'll have wire here And so what will be happening as the current's flowing toward us, the lines of flux are going to be going around the outside of it like this, and they're going to be going like that. And when we have them close together, these guys are going to be flowing around together. So as these guys are going this way, it's going to be, this one's going to go here, and this one's going to go here. So these guys are flowing together. They're kind of matching up. That's what we're talking about. Now, when we talk about eddy current, it's going to be, okay, well, instead of having these two nice and close, we're going to have one over here. As that pathway continues to go through, these are getting farther apart, so it's easier for these lines to mess up against each other. And where this guy was going here and here, now this outer line, opposite, and start to form in your mind. You see eddy current, you see a little swirl inside of the lake, right? Well, that's exactly what's going to happen in there. That invisible line of magnetism that's happening out there is going to start. And we can avoid those by moving it closer together. Is all that's going to say. There's much magnetism motors right now too. So everybody clear on eddy currents. You're not going to spend a lot of time with eddy currents in the HVAC world, but if you ever spend any time with transformers and or electric motor rebuild, which that you guys are ever going to rebuild the motor on your stuff, you'll most likely just throw them away and buy it because it's not cost effective. All right, let me see what Kenny had for notes on that one. Let me go up one. So there are many different types of transformers for many different applications. Large power transformers are designed to operate at electric utility voltages from 115 volts to several thousand volts. A common use for some smaller transformers is to provide low voltage AC to rectifiers or conversion to DC. Rectifier transformers. Air conditioning systems use low voltage transformers to provide 24 volts AC to control circuits to operate relays and solenoids. These step down the voltage from line voltage, which would be 120, to 24 volts and are referred to as control transformers. Transformers will heat up during operation. This production of heat is insufficient. Transformer cores are made up of thin sheet metal strips in the form of laminate. There are a number of advantages to using these thin metal strips. It's far easier to manufacture thin sheets because they can be stamped, where the thicker material would have to be cut. Also, the voltage induced in the core current, called eddy current, to circulate. All right. So what they're trying to explain to us with that part right here is, as we're looking at this particular guy, you can see these are all just laminated, really tiny thin strips. In there to try to make it easy, first of all, and then apparently that eliminates some eddy current too. You guys need to see that? No. Okay. Pretty familiar with those. Beating a dead horse with transformers, huh? Sorry, not my children. Okay, well, just in case you thought we were done with transformers, let's talk about their construction and operation. See, to me, this should have been in line with the other stuff that you need to talk about for transformers. So, okay, transformer construction and operation. The left picture here is an industrial control transformer with a kVA, so like a 500 watt transformer. The low voltage secondary windings are heavier than the high voltage primary windings in the control transformer because part of how, so we know that we're transmitting voltage through that system, but we're also transmitting current through that system, and it's proportional to it's similar to the turns ratio, except for that as the voltage goes down on the secondary side, what do you think is going to happen to the current? They're inversely proportional. So voltage and current, absolutely. It's absolutely what's going to happen. As we reduce the voltage on a control transformer down to 24, we just know that there's going to be a little bit more current hanging around in here, and that's typically why we don't have a lot of loads or volt control transformer, and that's hence control, is that we're only going to have switches there because those don't have any real load. It's just the opening and closing of the sensing device. So transformers are commonly rated by volt amp ratings. With VA, the VA is literally the voltage multiplied by the current or power, or that could also be considered wattage. I think Charlie calls these sometimes a watt transformer. Same thing. That's probably more HVAC street lingo picked up in the hood. You know, Charlie is in the hood. So volt amp ratings or watt ratings are used because they apply to any load, whether it's resistive, reactive, or a combination, which would be called impedance. You guys remember anything in your first year about impedance? No.
I remember that word.
You remember the word? Basically another word for resistance in an AC circuit. How about reactance? You remember the word? We'll talk a little bit about it maybe once we start talking about the actual coil on the contactor. It's tough too. I wish, yeah, darn it. Okay, next year, right? Sorry, fellas. Let me write that down. A lot of the stuff that I'm talking about is like these, when I talk reactive resistance or just resistance, or the combination of either two is stuff that you guys should have probably picked up in your first semester in your theory, your AC theory. You'll be fine. You'll be fine not knowing it. It gets kind of tedious, but it's definitely something if you want to know, it's probably something that should have been covered, but you'll be all right. Note that the amp draw of the secondary is much higher than the amp draw of the primary. Take, for example, a 48 volt amp transformer with a 120 volt primary and a 24 volt secondary. So let's do that. Everybody see it if I write it over here? You guys got it? You see it, guys? Yeah.
You raised your face.
Is that what I drew?
Yeah, me and I both know.
All right, so primary current. Our primary current is going to be, so P. Get that out of my face. Expo, let's do an orange. Maybe that's new. D-eyed. Blue. Well, there's something there. All right. So our primary, so I, P equals 48. Should we do volt amps? Do volt amps, or we can do watts. Same thing, except for this is volt times amps, which equals watts. So that's our first, and then we have our 120 volt. We're going to have, this is voltage on the P primary is going to be 120 VAC. Okay, so the primary current, 48 volt amps divided by 120. So what we're trying to figure out here is we're trying to figure out what the current is on the primary. So I equals SP, which would be power, or volt amps, or watts, divided by voltage. So our voltage we know is 120. So power is, this is what it's going to be. I equals 48 divided by 120. Who's got a calculator? You got it? What this transformer that is in our head is going to consume 0.4 amps. So the secondary current equals the same. So power in equals power out. So 48 volt amps is the same that's going to happen on the secondary. So we're going to put secondary, let's do I of S. I of S equals 48 volt amps. But our voltage on our secondary is going to be different. It's going to be 24. So now we have a clearly different setup here. We have 24, 48, which equals, Donnie, 2. So there we go right there. And this is all. Did Donnie didn't answer?
No.
Dang it.
No, Chris said.
It was all Chris. Dang it. So what the big picture here is,
Hold up. 24 divided by 48 is 0.5.
who's doing the math over here? Yeah, I asked Donnie. 48. Trying to figure out, so we're trying to figure out what our current is. So the power divided by 24. Oh yeah, my bad. My fault.
Did everybody all
Wound up. Yeah, no kidding. I'm gonna get thumped. Okay, 48. It's a good thing Steve's not here. I'd be getting yelled at. 48. Yeah. Let's see. VA divided by 24V equals 2 amps. So what is happening here? What's the relationship here? We have on our primary side, so IP we have equals, what was it, 0.4? Yep. This is why it's important to show your work neatly so you remember what your answers are. Yeah. Man, there sure seems like there's some sort of a relationship right there, right? Like if we were to have 120 divided by 24, what would we get? A ratio of some variety. Do I got to do it now that everybody's mad? We're running out of room here. Get out of here. This is the last month for it anyway. Okay, so our ratio there is 5 to 1. So let me think about this a second. So we have 1 down here. So 1 equals 2. What do we think we got going on here? What's the ratio? What's the equation there? We remember? Then we have to do something like this. Yeah, I don't remember it either. We're not going to do that. What I'm trying to illustrate here is that power in equals power out. So this is probably, I bet we can take 0.4 and times it times 5 and probably get something right, huh? Like maybe 2? Be my guess. How do I clear that calculator? So 0.4 times 5 equals 2. That's the relationship that I'm trying to illustrate. So 2, and this is, golly, I thought that's what it was. Yep, that's what it is, 4. So I think it's cross multiply and divide, maybe. Ain't that what that is? We're not going to pay attention to that anymore. That's math.
That was the last semester. We don't do that.
Yeah, let's get rid of it. Okay. Well, now that we're square with transformers, and I've probably skipped ahead several slides, we're going to review low voltage transformers, maybe. Just come right in, Jason. We're not having a class here or anything. I think this is telling us that it's agreeing with us. Note that this example ignores heat given off. That's why the secondary winding is made of a heavier gauge than the primary winding. That, and there's going to be more current on the secondary winding. You're talking 0.4 and 0.2 volts. You could have some pretty small wire to be able to handle 2 volt amps, 2 amps, 0.4 amps and 2 amps. You could have some pretty small wire to handle that stuff. That's why we get away with, when we do have a secondary side of the transformer, you guys get away with thermostat wire. It's not rated for more than 50 volts because the insulation is so thin. All right, moving on. Everybody clear on transformers? Beat the dead horse. Let's review some low voltage thermostats. System switch. We can have it either in the fan and either on or auto to come on whenever the on, or if you're farting too much, you can just turn it on and blow the house out a little bit. Yeah, actually. So what we just did in the electrical motor lab is we made electromagnets, which are essentially the same thing. So if we were to put the electromagnet up against another electromagnet, we would induce a voltage just by having it there. It would be incredibly small. The voltages that we were using for our electromagnets were like 1 volt, maybe 1.5, to make the iron core magnet. If we had the perfect system, and the problem with that is that we're using DC voltage over there. So here's our coil, and then this symbol right here indicates a magnet or an iron core. I think it's just like that. I don't think it has the ends on it. So that's what we built right there. We built positive and negative. So as the current flow is going through here, we're making those lines of flux. And if we were to set another there, it would do exactly that, make a transformer. It would go. But except for the difference would be that as the current is flowing through here, this direction, the difference would be, it would be the exact opposite direction down here. So as current's flowing through this way, it would be flowing through this way down here, because it's a law. I believe it's Lenz's law. I think that's what Lenz's law is. That as this coil here is intersected by these magnetic lines moving this way, this voltage is going to be induced the opposite direction. So, but yes, long story short, we just made transformers in the form of an electromagnet. So don't get me started on electrical stuff. I can dark out all day. It is neat, and the whole thing about it is that such a very simple thing. You guys played with magnets when you were a kid. I got magnets out there we could play with all day long if we wanted to. But that's what we're using all around us is magnetism. Even in these ballasts and the lights of magnetism, there's transformers in there. You know, it's just like, if you think about such a simple theory is what makes the world go around. You know, it's magnetism. That's all it is. It's so neat. And you know, that's why I get all wound up talking about it, because it is so cool. You guys got me all fired up on magnetism again. I just finished that class off yesterday, and now I'm back in it. All right, let's get back to where we were here. Anybody have any questions on thermostats? I think we've probably covered them good enough, and we're going to review Thursday, so we don't need to really spend any more time with that today. This guy, the only thing I'd like to add, see this? Thermistor. It looks a lot like that small diode, doesn't it? Yeah, I'm not uncertain that it's not. They do look exactly the same, man.
I was just gonna ask how it works.
Thermistor? Should have found one. Let's read about it.
Google it.
Let's read about it. I believe what it is that as the temperature rises, and I'm gonna guess that as the temperature rises, more voltage or current is allowed through that in the direction that it's going. But I like the question. We'll find out about it. Google. Let's see. How? EOE. We want to know how it works or how it measures temperature. Okay. Magnetism. Don't get me all wound up. We're getting deep. Okay. We're going to go deep on a thermistor here, buddy. Ooh. Okay. All right. I hope she wasn't saying it was about a thermistor. It'd be weird. There it is. All right. So thermistors are like an RTD. Do you know what an RTD is? Resistive. Let me think. A resistive temperature detector, I believe, is what RTD stands for. And all they are is we use them a lot in the electrical world as a heat sensor. Like if we wanted to monitor a bearing of a motor, a huge motor, we would put an RTD right there, and we scale our sensing program to whatever zero is, coldness, and then we just scale the voltage decrease. It's not a voltage decrease, it is in the sensing sense, but as the RTD gets warmer, the resistance goes down. So that's basically what it is it's a.
Is it basically just like a different metal alloy that affects?
I'm not sure what the internal is. It's a resistance that changes, though. I do know that. Yeah. Well, let's talk about a thermistor before we talk about an RTD. So it says, like RTDs, thermally sensitive semiconductors. Semiconductors. That's what one it is. Whose resistance varies with temperature. That's kind of what I assumed it was, is that it's very similar to an RTD where as it gets hotter, the resistance changes and allows more voltage to pass through. And then the system is set up. This little fellow here has got the circuits in here to Good thing we got a bunch of them on the shelf, right? Well, where's the thermistor at? Yeah, I saw some stuff rolling that way. Dang it. That's coming right out of my check. On back there. I know there's a thermistor in here. Maybe that's it right there, huh? Which doesn't look the same, but maybe that's an LED. I don't know. Tough to say. Tough to say just by looking at it. But yeah, definitely. So wherever that guy would be in this system, all of these little circuits down here are all set up to change or to sense that current change in there. So you might as well have a look at this. You know, we opened it up real good. Yeah. So thermistors are manufactured of metal oxide semiconductor material encapsulated in glass or epoxy bead. Also, thermistors typically have much higher nominal resistance values than RTDs. I will say that most RTVs that I've measured with my meter have been around 120 ohms, 100 to 120 ohms. And that seems to be much higher. Anybody, let's see, anybody got their meter up yet? Nah, I'm curious.
I have it.
Got it. Let's measure what this is. Oh, yeah. Does that make, just like what we're talking about here? But this is also, the thermistor is also going to be directional. So, see what this little devil reads. I assume what we're going to have here, since I'm assuming this is a diode, we're going to be able to read an ohmic value one direction, and we're not going to read it the other direction. So we have a resistance there, which means it's very high, though. It's very high. And then once we change the polarity of our leads here, we should read. Let's see. That right there is. Check. So we're reading nothing there. Now I should be able to read it on this one. Maybe we don't have that. Is that if I hit that red button, does that mean that that's what's happening?
I don't know.
Yeah, red one changes it to red.
Sure. So we definitely should be able to pick up something one like this. Unless we don't actually have what I thought we had. So, go back. And what was got the experiment? Okay, nothing there. Nothing there. Let's go back to this. This may be it there, missed. So right there, we have 1.13 meg ohm, and now we're rising. It might be.
Because there is a detector.
Yeah. Yeah, look it up, we're so smart. There, well, we may have a thermistor. We would expect this to have a very high resistance. Yeah, I think this is it.
So there's not no little lines like a diode.
Well, there is the one line, but it looks like in that picture of the one that's online with that thermostat, this looks like the exact same thing.
Oh, man.
And see how it is a little bit different than the diode we have here, the other little diode. See, it's a little different than that guy right there.
Yeah.
That's what I was saying. Yeah, it looks very similar.
We don't have that little thing.
I might have brought you guys a thermistor and didn't even know it.
Yeah.
Go me, huh? All right. Okay, now let's get back to work here. Let's get back to plugging away. Exit on that, and let's bring this back up. From current slide. Okay. So if we're good on thermistor, it's a high resistance that changes. And there, I did see on there that there's two different ways. It's either an open on resistance, like as it heats up, the ohmic value increases, or as it heats up, the ohmic value decreases. So there's two different styles. Now we're going to talk some more stuff about low voltage thermostats, touchscreens, and all of that jive. We don't need to worry about touchscreens right now. So line voltage thermostats. We talked the other day about why the difference is because of why our voltage ratings and our current ratings are much higher on a line voltage thermostat than they are on a low voltage thermostat. Remember that? We drew it up on the wall. Why is it, Chris? Because on the line voltage side, we're switching a much higher amount of current.
Yeah.
They're typically going to be in line with the heating element, where I've seen the most of them. instead of just closing the switch to tell the system to come on, the line voltage thermostat is actually going to be the one that's doing the work. It's actually closing to bring that heating element in line. So I think you guys remember the little drawing you wrote up there? Yeah. No. All right. Then how their operation is, the sensing bulb is going to have a volatile liquid in it that's going to go up, or volatile, did it say volatile liquid? I think it did. Remote bulb thermostat. I think that it did say volatile liquid if I remember correctly, but it's going to, as the temperature raises, the liquid is going to turn into a gas. And it's going to increase the pressure inside of this tube. It's going to activate that little switch right there, the bellows. And here's where have you guys seen any of these? I've seen a gobble of them on those circular radiant heaters. Just that's pretty much all you see on them. You've probably seen a lot of them in the shovels. Back of the shovels. Yeah, that's what they use to control them. Just very simple. It's a very simple deal. It's once it gets too hot, it's going to open, and once it gets too cold, it's going to close. And the capillary type thermostat, this guy's actually, the difference between these two is that this guy is actually going to move a switch, and it's enough pressure in there to actually move the switch inside of here instead of just moving the bellows, and the bellows is what moves the switch. That's the difference. Everybody's got that now. Relays. Now we're going to talk about something new. Relays. Each one of these little devils that I have right here is a relay. They look very much the different. Some of them are similar, but this one especially looks different, but they all do the same thing. Control relays. These guys down here. You will see some of these in your bigger units. I don't know if they're small, just standalone heaters or stuff like that, have any unpluggable relays or anything like that. But right here, visible coil in the front. Visible coil of fine wire is part of the electromagnetic arrangement of this relay. So let me see that one real quick. Right here, if we're looking into this, we're actually not going to see the coil because it's going to be covered with the black circular cylinder inside of there. That's actually going to be the coil in this one. You can see the wires in that one. Though. Very thin, like hair strand stuff in there. And this guy right here, this is a solid state relay. And I think that we read stuff in there about relay logic and solid state logic. That right in here is the difference between those two. That one actually has coil that we're bringing in. This guy right here, all he is just some semiconductor material in there that's either going to switch when the voltage is high or not. In this case, we have a normally open and normally closed. So whenever the voltage is high, he's going to activate and he's going to open the normally closed and it's going to close the normally open. So, and it's all, there's no movable parts on these. It's all solid state. This thing right here will last a long time. So, if you do pull this out, let's be careful when we put it back in because these little columns down here are easily bendable. So it'll good when you go push it back in. Let's see what our notes are. An automatic switch requires some method for opening and closing. This is often accomplished through the use of a relay. A relay is an electronically open switch that uses an electromagnet to open or close a set of contacts. About how much of your relay stuff that you guys have gone through, so I have a little text here for us. This is actually what's going on inside of most relays and the foundation for what's going on inside of the contact. So what we have going on here is exactly what I drew on the board over here. We have an electromagnet. We have a coil of wires going around an electric core or an iron core, a magnetic core. And what we're going to do is when we want this relay to pick up, we're going to energize this electromagnet. And when we do that, that's going to grab this little boomerang here. I believe they call it the armature. pointing at right there. And that's going, once this moves in on that pivot, it's going to push this up. And then this is going to go from being a normally closed set of contacts, it's going to open contact with the normal open set of contacts. And that's what's happening inside of this relay. You guys all square with that? We use the magnetism to pull in that little. Oh, dang. Okay. Here's their graphic on what's happening. Right here, it's showing the coils de-energized. The contacts are held closed by a spring force. Coil is energized. Contacts are opened by the magnetic attraction of the coil. So let's read what they have for notes here. Relays can be designed for normally open switches or normally closed switches. The excuse me. Oh, that's just on me. All right. The normal position of the switch is always the position of the switch when the relay coil is de-energized. So keep that in mind. When we're talking a normally closed switch, it's going to have continuity between it when it's de-energized. And in order to open that switch, we have to energize the coil. A lot of this stuff will definitely play a part in your world, especially opening and closing of contacts inside of your equipment. So always when we're talking about the contacts on a relay, when we're talking about them, we're going to assume that they're in the de-energized state when we're talking about them. So let's see. It says here a figure, but I know that figure's not right. It shows a normally closed set of contacts. As the relay coil de-energizes, a spring is used to hold the contacts together. I think it's talking about this setup right here. When it's talking here, that's what we're talking about. So let's see. A spring is used to hold the contacts together when the coil is energized. Okay, let me see here. This isn't, the sentence structure is not making sense either. A spring is used to hold the contacts together. When the coil is energized or supplied with a current, a magnetic field is set up that attracts the lower contact toward the coil. This will separate the two contacts and open the circuit. As long as the current flows through the coil, the relay is energized, remain open. All right. Everybody pretty solid with that portion of this? When we energize the coil, it's going to activate the motion inside of the relay. So now we're going to talk about contactors and starters. A fan relay, a three-phase contactor, a single pole contactor, and a motor starter. Large amperage systems that may have multiple contactors all wired together. So right here is what my example for that is. Here you'll see here a valve. This is just a regular old three-phase motor contactor here. Nothing special, nothing fancy. This is just going to pull a three-phase set in and drop it out whenever the coil is energized or de-energized. You can mess with this. You can see the magnetism that's on here. When we get our tools out after I get done blabbing here in a couple minutes, we can pull this part and look inside. You can actually see the contacts on here. So pass him around, and then here's the big daddy. This is actually, we'll spend a little. I'll send him around, and we can probably just see it all pretty good from here. But this is an actual motor starter with a set of overloads here. These are the overloads, and we're going to talk about those in a second. But so like a breaker. These have a set of, well, they're actually even very similar to the thermostat. This thermostat right here, how it has the bimetal internal structure here that is going to move as the temperature changes. That thing is almost exactly what's happening inside of here. So as these overloads are set to go off at a certain temperature, but as the temperature is rising, that from the heat from the current going through there, that little internal coil is going to expand, and it's going to expand enough to where it trips. There's a little lever inside of there, and as it expands, it trips that lever, and that's what sets this overload off. And These are usually wired in line to kill the whole starter, so you're not single phasing the motor. But you guys can. This one is especially cool because as you activate it, you can actually see the plunger, the electromagnets back here, and as the coil layer does, it pulls that plunger down into the little contact. You can send that back, I suppose. Okay. And all of these things, the relays and the contactors, they're all virtually the same thing. The difference between them is the amount of current that they can carry. So obviously, a lot more heavy duty work with this starter that Steve's got than we got with the small relays back there, just from looking at them and knowing how some stuff works in life. So this controller very small. Front view of the contacts, that's not a super great picture in my opinion. Apart. Contacts for control relays are often very small because they do not need to be connected to the load, since they are typically only relaying a signal. Typically, a relay contacts are rated for 15 amps or less. Contactors that are connected to the load will need to be larger. We see the difference of that going around right now. There's another kind of picture of what's internally happening with the big contactor that Dennis has got. There's a picture of the ratings in the middle there. Actually, what it looks like when it's all wired up. Operation of a contactor is shown. There may be one or more set of contacts on the armature. The contacts are rated by the voltage and current they can switch. They are normally ratings, resistive, FLA and LRA, the full load amps and load running amps would be those ones, I assume. Motor starters work on the same magnetic coil principles as relays. Lock rotor amps. Okay. All right. Motor starters work on the same magnetic coil principles as relays and contactors, but the actual contact size will be greater. Contacts should snap open and close with a spring assist to reduce arcing across the contacts. A magnetic starter is shown. So that's something that you're definitely going to see a lot more on that Big Devil than you are on the small starters, just because of the happening whenever, especially if we're just opening and closing a motor load there. That one, I think that's a 30 amp starter there. So the time that we decide to turn that motor off, that starter, when it opens, is going to have an arc of 30 amps that it's leaving open. That's why it's important for them to have that spring stuff on there. So this is the beginning part of when we're talking about overloads. This looks like an internal motor overload here. I'm not going to spend a lot of time with that because there's not a lot there. You can see these sometimes on compressors will have them. They'll have a little motor internal overload. And a lot of times on what I think Charlie was talking about in this class was talking about checking your motor cold. Did he say that in here? Or was that the other class? Okay. So if we get called to a service call to troubleshoot why our fan's not spinning, and we get there and the motor's so hot we can't touch it, and we read it and, oh geez, we got an open coil here. It's important for us to let the motor cool down to ambient temperature and then recheck it again, because a lot of these motors that you guys are going to experience are going to have an actual, it may either be of some variety. It's either going to be a current overload that's going to go off of a high current, or it's going to be heat overload. It's going to go off of high heat. Either thing is basically the same thing. If you have a high current, you're going to have a high heat, and it's pretty tough to have a high heat without a high current unless you have a bearing issue. And the bearing issue is easily solved just by spinning the rotor. So a heck of a lot more time on that, but you'll see those. That's just a common sight that you'll see. So line duty overloads and pilot duty overload relays. So right here, a thermal overload is used to protect electric strip heaters from overheating. Typically what we would call that in the real world is called a click-on. It's just an open and closed thermal switch. Very simple. When it gets too hot, it's going to open. When it cools down, it'll close to allow that strip heater to work. Bimetal current overload used on a small hermetic compressor. I believe that that's very similar to what you're going to see with that picture on the front with a reset button on it. Thermal overloads, let's see. Thermal bimetal overloads used with electric heaters are good examples of line duty overloads. They open to break the circuit to the heater if the strip heater overheats. Loads are often used on small hermetic compressors. I see these a lot in electrical boxes that have like a box similar to what we have back on the wall that have pneumatic. You'll see a lot of those in them, just to keep, especially if it's an outdoor location, just to keep everything from freezing out. It just gives it enough heat inside that box and to keep the airlines from freezing out. Here's an example of a pilot duty overload relay. This is basically the same thing that we have in the big contactor there. Relay is another type of pilot duty overload. The advantage of this type of overload is that it's only slightly affected by ambient temperatures, therefore avoiding nuisance tripping. So usually when those guys trip out on our big contactor back here, it's because we have an overload. And most likely if they trip out, it's because we have either a short in a winding or we have a phase-to-phase fault inside of the motor itself. And finally, the summary. So resistors and capacitors are commonly found in most circuits. Capacitors we didn't talk about. Transformers have a primary and secondary winding that can be configured to step up or step down the voltage. About fuses and circuit breakers, they're current limiting. Switches, relays, and contactors are used to open and close circuits, and relays can be used in combination to start, stop, and engage safety circuits. So I did have you guys read in here some stuff about relay logic and solid state logic. I do want to talk to you about that, but I feel like we've talked enough today. I think we got 30 minutes or so, 40 minutes. Let's what I really wanted to have happen is go a little bit off of what we showed here, and I want us to look at our lab number 34, or maybe 35, yep, 34-5, identification of relay and contactor parts. That's the main goal. What I wanted to see us get done today was just make sure that we went through that. And there'll be some meter stuff, so if you want to grab your meters, you can identify. I'll put a relay in a coil at each table, and then we can talk about each individual one. What meters are there? That's fine. You guys, yeah, go ahead. Just grab your meters. Take your table. You need a meter, Don? No, my battery's dead. There's a motor right there. I think. Is it just a 9-volter? No, it's 2 AAA. 2 AAA. Wow. That's a tough one. That's a tough one. I don't know anything about AAA. I have my little card, I'll just stamp it for you. Huh? No, I got it. Yep. This is your lab time, so I mean.
The PowerPoints, they're all in zip files, so they're extracted. I'm gonna download all of them for both editions to my computer. And I think we need to de-inventory the share files before I have anything else to them.
Anything, I'm getting over what my other two classes will be. I think it's 121, and then, I don't remember what the third semester class was, but I'll move everything that I want out of there, and then you can do whatever you want to do with that.
I'm probably gonna have that in there, just let it waste hundreds of those folders. They must be automatically generated.
I would have to say, I couldn't see anybody
Because I mean,
really having a. Do you guys have any AAA batteries?
I believe so. Hold on, there's some out in the supply room.
Donnie needed them for his meter.
I'm letting him use mine.
Probably looking for some batteries for you guys. You guys had to have a stud finder too?
No.
Oh,
No, I had one for the summer. Cassette installation.
I figured you for a stud finder.
Well, it worked every time I use it on myself. But I never worked on the wall.
When everybody gets back in here, we can get started on this lab here. What my main goal is for you guys is to just spend some time with the computer meter and drainage water. So I think someone would always have a little diagram of that. Yep. So right, that line right there that your finger's on, that is the core. Yep. And so your voltages are going to be down here, the these are the different numbers for the set of contacts on here up to the little pointer. Okay. So what we've got going on here is clearly is, so number 1 to number 4, and then we set from contact. And so point 4, from energizers, this set of contacts is going to be from 1 to 7. Yep. Yep. I think it's a screen, it's going to suck it to it, and what the action is going to happen right down here. So this, the top section here, that's going to get broken, and it's going to go to the bottom section.
Right now, every 1 to 4.
Yeah, you should see a coil. Yep. 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 That should be exactly right. And I've seen a lot. When these things get older and they switch a lot and they start to stop a lot, these contacts will actually get wired, but actually not moving. Yep, because of the little, it's not in. I wish that we could do it, but not that. He's a $100 kind of guy, huh? Yeah. All right. So, this is to switch it on the contractor. There is there's a little bit higher amount of spark that happens, just how the coil wire reacts instead of just having it.
See that school line? She's gonna go work for Trump.
All right.
She's gonna be secretary for. Awesome. Yeah.
Man, I feel like she should maybe be like the secretary of the mining or something, right?
She's got.
Oh. Can you get your laptop for you or what?
Just download all these,
All right, so if you guys want to get started with going through these contactors, I encourage everybody to get their hands on them. Dennis had a nice question about the ones he's working on right now, about the little diagram that's on these. You guys have a diagram on yours too. Each one of these smaller ones does have a diagram, and you'll notice if you kind of follow up the different dots here, this particular one, they're not numbered up here. You'll be able to tell because this one has a little knob on the bottom where it plugs in. If you look at these, the internal contacts are right there on the side. So if you follow that down to underneath, you'll be able to check out the different contacts and then actually be able to check out the coil. You won't really get to see it until you see one of these. So this guy, right here, this is going to be your contact side, and this is going to be your coil side. So right here from here to here, you should see a coil. You should see a small voltage, or excuse me, a small resistance. That's a huge. That's a you can take that one apart if you want. You can't really do much with the smaller ones because they're like the ice cream relays because there's you can actually with this guy you can measure him the base too. And that's just these screws are the same contact. There you're right. There you can identify here. And so this is going to be the common contact right here. So you can bring at least one side of the switch into here, and then this one's going to be the normally closed because of this coil here, and then this guy's going to be the right here. So when we're making the switch, this is the electrical motion that was bringing the switch. Now we're either going to have a circuit going from here that we're wanting to hold it when the switch comes on, or we're going to have the ones from here to here that we want to close and the switch goes So you're thinking, I think you're thinking of it in terms of where there's two separate sides. So this side doesn't have anything. So this is just basically to energize this guy and allow it to be able to work. In this case, we have to bring the power to the switch, right? So you're going to have a voltage up in here, either make it through on this side all the time, and then energize the source before you'll bring it through and have it just and energize this one. So internally, what we have here is that. So let's just say this is. Say we're just gonna have a push button. This is a push button. So whenever we push the push button up, it's going to send the signal from here to here to pull this in. Scott? Okay, more of it. Thank you. Yes, thank you. I used to say to you at one time too about our friend Josh. So probably over 30 or 40 minutes. All right. So sitting around, we got this one on here. So whenever we energize this coil, And we have the cross here, and that's, and 3 wires that are coming over. So, in this particular setup, we
What's your last name?
always have to have voltage coming to the switch. So this is
Is it just one person? Is there a lot of people?
So, we're gonna have, this is basically working the same as a light switch. So we're gonna bring our power into here, and we either have the option to come over and have that power come to here, automatically come out on this as we're manually closed side. So this circuit is gonna be made when the switch is off, or we have the ability to have this come over here and make this when the switch is into this. So whenever we hit that push button to bring that coil in, it's gonna either open here or it's gonna close here. This is 12 is here. So I make it a little clearer. So,
You still.
it can, if we want. Yep, it's just gonna close this switch and open this one. That's pretty much the long and short of that guy.
I'm just one model.
Yeah.
Line.
You get it apart?
Yeah, I was thinking about it now.
We located the, or identified.
Yep.
So electrical connections to
Yep. I'm gonna be right up here on the top of this. Typically, that's what it's on.
the armature.
Armature is going to be the actual movable part. So this is the armature right here. Yeah. Yep. I want you guys to just have a experience to look at several of these and kind of run meters through them a little bit.
How many contacts does it have?
Check if it's, to see if it's good meter wise. Just
So that's how you check your coil right there. So let's do that. Let's go to ohms.
It's diode, probably, should be on top. 130 ohms.
Yep, that's what you should see there. You want to see a resistance across there. So there's, we know just by looking at these and how they're going to go in here, this has no contact to this, so we're not going to do something here. I'm checking across here. The only time you would check across here, or you had a voltage coming into this system. So in order to check to make sure these contacts are good, you're going to go this way. And you can see, because if we look kind of sideways down here, you can see the little development down in there. Those are the actual things that are going to contact. You should see number 1 going across there. Yeah, we basically read the wire, and that should work through all of the little stuff there. When you guys get on that down, we put it back together. Yes, thank you. Everybody doing okay with that stuff? If you get finished looking at one, send it around to the next table.
It says how many contacts, is it 1 third, or is it?
No, it's when it's talking about contacts, it's talking about the actual. Yep. Yep, yes, sir. So this would be a 3. Yep. Each one gives you a set of contacts. Yep. These ones are fully linked. Yep. This looks like a sweet place to land some torque terminals or some reverse spades. What do we call those? Yeah, female spades. You done with your big one, Donnie?
Yeah.
You don't know how to do it? So,
I mean, you don't need that.
so when we're talking the coil, the coil is gonna be these two wires right here, they're gonna guide back into the back here, and we can't see. Instead of the contacts on this guy, are actually, this is where our three phase is gonna enter into the system, and then through the starter and the overload, this is what's gonna exit down here, so the contacts, we should. And so we should see a nice. And you should be able to read all three of these the same way. Yep, and then so check each side. This is the coil, we expect to see a little higher. Maybe that's not. We're hoping to see something like around 100, or maybe a little higher. How about this one and this one? Put them up here. There you go. This one. Yep. That's where they're pulling this one. This is
That's like a sense of
set up because what we got going on here,
no moving parts
but
inside.
wires control. These are overloads like we talked about. What's up, buddy? So, yep, that's a set. And then this is the, here's a set.
Sensitive.
Yep, right. Yep, sir. So now we're going out to the lab. Now these have, there's 6 contacts for this guy, or excuse me, 3 contacts, 1 for each phase. This little level here is like one second here. All right, I'm glad you guys are excited about relays. I like it. Relays are really fun.
Oh, yeah, we can.
Don't take those apart. Don't take the ice cube relays apart. This guy here, I'll just give him the picture. Here, take this one apart. This will keep you busy. Have some fun.
That's space.
Here's a set of contacts. Here's a set of contacts. Here to here. This is a normal close set here. We got some of this energized. That should suck down here. And this.
There we go.
All right, I think I can shut down my recording maybe. This is going to be quite the file. Stop.